Hi, welcome back. Today we are going to continue our conversation about multiple genes. We're in our genetic traits unit, and again we've moved beyond talking about Mendelian traits, and we are looking at the things that Mendel didn't know about. And you've already learned about how different genes can work together to produce one trait, and we've called that polygenic traits. We're going to start looking at a special case called epistasis. This is still part of your learning goal number 10. And you should be working along with me on Big Ideas, page 6. Epistasis is when you have one gene masking the effect of another gene. Sometimes an epistasis is when you need two different genes both to have a dominant allele in order to produce a required phenotype. So it's ways, really very specific ways that genes work together. Now, you've already been working on an epistasis example. When we talked about the Bombay phenotype, that is a type of epistasis. So this is one of the cases where something that's homozygous recessive on one gene, in this case the Bombay phenotype, has an effect on a different gene, which is the ABO blood type. So I want you to practice that. Take a second and use a forked line diagram in order to go ahead and cross two individuals that have AB blood type that are also both heterozygous wild type for the Bombay phenotype. So do that on your own, pause me, and then come back to me when you're ready. Okay, so hopefully you have gone ahead and done a branched line or a forked line diagram to cross two individuals that are both recessive and recessive carriers for Bombay phenotype, So they are heterozygous for Bombay phenotype, and they are both also AB blood type. And when you cross those, again, you do one trait at a time. You could have done whatever order you wanted, but here I started with the AB blood type first. So first we focus on the one gene. Two individuals that both have AB blood type are going to produce one predicted offspring ratios of 1/4 type A, 2/4 type AB, and 1/4 type B. And these are the offspring that we would expect to see right there. List those out first. Then take a look at the H substance, or the Bombay phenotype. If we're two parents that are heterozygous for Bombay phenotype, so neither of them actually have it, but they're both carriers, we would expect to see 3/4 of them would form 3/4 of their offspring would form a normal H substance, but 1/4 of their offspring would probably have this Bombay phenotype, which would mask whatever was going on with your AB blood type. So if you go down here, this 3/4 and 1/4 ratio is going to happen within each of these groups. So 3/4 and 1/4 of the type A group, same groups out of the type ABs, and same out of the type B. So multiplying across, 1/4 type A times 3/4 that will form the H substance, those will actually show the blood type. That means 3/16 will show up as type A. But whenever they don't form the H substance, or they have the Bombay phenotype, this A won't be able to attach properly, and that's going to show up as type O. So 1/4 times 1/4 looks like type O. Why? Because they have the Bombay phenotype. Then that happens again in this group. 2/4 times 3/4 will show us 6 out of 16 would show up as type AB. But 2/4 times 1/4 will show up as type O. They would have originally been a type AB, but because they have the Bombay phenotype, they're going to show up as type O. And then in this last group, 1/4 times 3/4 is 3/16 will show up as type B. And when you multiply 1/4 times 1/4, you'll get 1/16 that would have been type B, but because they have the Bombay phenotype, show up as type O. Now I think you'll notice with this that some interesting patterns. So I'd like you to go ahead and try to answer that question in italics for me. If you did not know about the H substance and the gene controlling it, what type of phenotype ratio would you have seen in this offspring? Pause me and then come back to me when you're ready. Okay, so in order to do this, you needed to add together each of these type O's. So again, you're going to have the 3/16 types A, the 6 out of 16 type AB, and the 3 out of 16 type B. But all of these type O's would have looked exactly the same to you if you didn't know about Bombay phenotype. So when you add them together, 1 plus 2 plus 1 is a 4 out of 16 type O. This ratio, 3 to 6 to 3 to 4, is what you would have seen. And that's a ratio that gives us a clue. Anytime we see this kind of ratio in our phenotypes of our offspring, we need to think automatically, ooh, this might be epistasis. And so that's one of the things that I want you to take a second and write down. Whenever you see a single characteristic, but for some reason the ratio's showing up in 16 parts with a 3 to 6 to 3 to 4 ratio, you should think to yourself, epistasis is occurring. Now, there are a bunch of cases like this that will help you see different examples of epistasis and different ratios that show up. I would like you to take the time to look at those cases and read pages 75 through 79, and then I want you to try to solve problem 417 that's on page 94. When you're looking at these cases, I think you'll find this diagram, figure 4-8, really useful. Again, it lists the different organisms and what character they're talking about, but it shows the ratio. It's different from the 9 to 3 to 3 to 1. This one's 9 to 3 to 4, and I think you'll see the 6 to 3 to 3 to 4 that we were just talking about today. These different ratios that when you see a ratio like this, it should give you a clue. And here's some nice examples that show you how they work. So do this, and we've got some additional practice on epistasis that will hopefully help you understand these types of genetic problems further.